Did Overbuilt save the day? France said the American Snowcat was a tank, wasteful, sluggish, obsessed with stiffness. Then came the Glacier no European vehicle had crossed. The irony was inescapable. When the crossing ended, the overbuilt American Snowcat stood alone on the ice. Every European machine was done. In this episode, we decode the engineering paradox, why heavy dampening and rigid frames, akin to camber-dominant boards with extra contact points, win when terrain turns hostile, fractured, and unforgiving. Stay with this, because the answer isn't brute force. It's controlled contact under load, and the systemic payoff when failure isn't an option. On paper, the heavier US Snowcat looked like a miscalculation. European fleets had already optimized the arithmetic that mattered to resort accountants. Lighter curb weights that kept bridges intact, smaller power plants that sipped diesel on long approaches, and modular cabs that could be swapped in a bay between morning grooming and evening transport. The system rewarded consistency and quick turns. The scale of the cost differential over a season was staggering. European design favored compact mass and efficient packaging. Lower weight reduced rolling resistance and track wear, which kept the maintenance ledger predictable. Smaller engines stayed in an efficient band for hours, not minutes, matching the duty cycle of resort grooming. Modular sub-assemblies, hydraulic pumps, electrical looms, cab elements, sat on quick disconnects. A failed valve block could come out in under an hour, limiting downtime to a single shift rather than a lost weekend. This was not romance. It was economics. Meanwhile, the American machine arrived with unapologetic mass, reinforced chassis rails that read like bridge work, oversized planetary final drives that many saw as overkill, dense dampening media in the suspension points, a power-to-weight profile that, by European standards, looked wasteful. The judgment came fast, too heavy, too stiff, too blunt. The irony was that every kilogram had a job. The ideological split hardened. One camp prized agile response, tight turning, and lower operating cost per kilometer. The other centered on redundancy under abuse. Components sized so that fatigue limits lived far beyond daily use. One side trimmed grams from cabs and brackets. The other thickened the rails. Neither side was confused about its goal. A simple analog from hard snow snowboard tech made the divide easier to see. Camber-dominant boards with carbon stanchions hold a line on ice. Rocker-heavy boards float and turn with almost no input, but they chatter when the surface goes loud. European cats felt like those rocker-heavy tools, quick, forgiving, and cheap to run on groomed hardpack. The American machine was a camber stick, stubborn under pressure, sure-footed when the surface glazed. Maintenance ecosystems reflected the same logic. European fleets leaned on parts compatibility and quick-swap modules. The virtue was uptime. Get back on the hill before the chairs spin. American fleets leaned on wear life. Bearings, gears, and track elements ran at lower stress ratios, so the odds of reaching a fatigue threshold were slim. You serviced less often, but when you did, the parts were heavier and the job longer. Each approach built a different operational culture. If this kind of engineering breakdown is useful, make sure to like the video and subscribe the channel. Resort operators saw the spreadsheet wins immediately. Lighter cats crossed old timber bridges without reinforcement, burned less diesel at altitude, and carved tighter switchbacks in narrow cutbacks. Those advantages compounded through a season. Margins widened. The narrative wrote itself. The tank-like US unit lagged in responsiveness, showed a dull turn-in, and carried a dead feel through the controls, effects attributed to heavy dampening and a stiff frame. But that critique stopped at the boundary of smooth terrain. It didn't address what happens when contact breaks and returns in milliseconds. Under shock load, when a tread unloads over a void, when a cross slope hardens to ice, when a bridge of refrozen melt collapses, the priorities change. Low mass helps you dance. It also lets the chassis oscillate. Loads move faster than the dampers can control. The paradox was direct. Efficiency ruled the resort, where failure tolerance was elastic. On a glacier, tolerance drops to 0. Controlled contact under load becomes the only metric that matters. The American machine's overweight reputation concealed a different intent. Limit rebound, stretch the contact patch, keep the driveline inside its stress window when the ground disappears. So the mockery formed in lift lines and maintenance shops, but the open question lived elsewhere. What happens when agile response meets fractured ice, hidden voids, and sudden torsion spikes? When the task shifts from groomed hardpack to a surface that punishes every shortcut in material and damping, the calculus flips. That's where the Glacier enters. An environment that erases elegant optimization and pays only for machines that refuse to flinch. The Glacier stripped the rhetoric. It offered a simple filter: survive the crossing or fail inside it. Hidden crevasses ran like trapdoors beneath a thin crust. Bands of blue ice slid under steel like oiled glass. Wind-hardened sastrugi carved ribs across the surface, each ridge a lever waiting to pry at a chassis. Micro-bridges formed by drifted snow collapsed without ceremony. Efficiency had no line item for that. The test was unforgiving because the feedback was instantaneous. A tread segment could meet firm crust, then a void, then polished ice in the space of a single rotation. When the segment lost pressure over a gap, traction didn't taper. It dropped, and weight shifted laterally with speed. Light machines, tuned for quick inputs, reacted as designed. They corrected. On glazed surfaces, that correction arrived too fast. The mechanics rewarded inertia that could be controlled. High dampening mass slowed rebound, so articulation stayed planted instead of hopping. The elongated contact patch, stretched by track length and tension, spread load across micro-variations in the ice. This was the same logic behind serrated edges that add bite on blue ice. More contact points, smaller slips, fewer catastrophic releases. The paradox was not mystical. It was contact physics. Think of magnetraction-style thinking, but translated to a track. Not teeth, but pressure nodes. When the surface turned brittle and the coefficient of friction fell, distributing normal force across more microcontacts reduced the frequency of slip events. Each micro-hold didn't add speed, it removed losses. Over hours, that math dictated survival. Low mass paired with rapid responsiveness brought a different risk profile. On a glazed side slope, tiny oscillations started at the nose and amplified by the time they reached the rear idlers. Articulated joints flicked from load to unload in quick bursts, which flashed through the frame rail as torsion. On groomed snow, those oscillations vanished into soft granules. On ice, they echoed. Failure modes followed a pattern operators recognized. Track spins scored the surface, polished it, and made the next rotation worse. Side slope slides began with a small drift, then turned into a diagonal runout as the uphill track unloaded. Lighter frames saw stress concentrate at weld toes. Torsional spikes created hairline cracks that lengthened under vibration. Gearboxes took the hit next. Shock loads from sudden traction changes pounded tooth flanks, raised oil temperatures, and pushed bearings toward micro-pitting. The heavier American Snowcat muted that cascade. Mass and dampers worked in sequence to blunt the first oscillation, then the second, until the system fell back into steady contact. The tracks maintained pressure through intermittent voids, not by crushing the surface, but by refusing to bounce. The driveline stayed inside its stress window because torque didn't surge in spikes. It climbed and fell in controlled ramps. This wasn't force for its own sake. It was time control, slowing the rate at which energy arrived. Even crevasse bridges, the most deceptive element, exposed the divide. Weight alone could punish a weak bridge, but the longer contact patch and the damped approach spread load and shortened the shock. A light machine might touch down harder after a partial collapse because it rebounded into the next step. The heavier unit accepted the sag, bled the energy through dampers, and rolled on without a snap. The result was stark. Controlled contact, not raw torque, explained why one machine crossed while others stalled or broke. Variance killed progress. Stability preserved it. The Glacier didn't care about fuel economy charts or nimble turn-in on groomers. It demanded pressure where it mattered, continuity when the ground disappeared, and a driveline that could ride the whips without spiking. Now the frame, the gears, and the tracks take center stage. How architecture turned mass into survivability. Overbuilding in this context meant a machine that refused to panic when the load turned ugly. Critics pointed to 5 culprits: a reinforced box-section chassis, oversized planetary final drives, steel-backed rubber tracks, multi-stage hydraulic dampening, and redundant cooling. Each looked like dead weight, surplus metal with a maintenance tax attached. But the Glacier assigned consequences to every shortcut. Take the chassis. A box-section frame resists torsion by enclosing the load path, not just thickening a flange. On fractured ice, torsion spikes arrive without warning. One corner sags into a void, and the opposite rail takes a twist. Lighter C-channel frames deform, concentrate stress at weld toes, and start a crack that grows with every oscillation. The reinforced box converts those same spikes into elastic work, then releases them through the dampers, not the steel. The result is boring behavior under stress. Boring is survival. Planetary final drives earned the oversized label because the gears and carriers dwarfed what daily grooming needed. But gear tooth spalling doesn't announce itself on smooth hardpack. It appears when traction breaks and returns in a jerk. Larger modules spread tooth load, slow Hertzian contact stress rise, and hold an oil film when torque surges. Micro-pitting never starts. Temperatures stay below the threshold where additives fail and bearings keep their preload. The driveline lives to see the next shock. Steel-backed rubber tracks carried the same indictment: heavy, overkill. Yet rubber alone delaminates when tension fluctuates violently at crevasse edges. A steel carcass disciplines the belt, keeps pitch accurate under mixed loading, and preserves the elongated contact patch that the Glacier demanded. You trade grams for integrity of contact, and with it, predictable steering under glaze. Dampening wasn't a comfort feature. It was strategy. A heavier sprung mass matched to multi-stage hydraulic dampers slowed energy transfer, so traction didn't fail in a skid and snap sequence. The damper stack, high-speed compression to catch hits, rebound control to prevent pogo, turned chaos into ramps of force. Skid events shortened, rebounds stayed inside articulation limits, and the chassis avoided the whip that shatters welds and spikes gear loads. The board analogy holds because edge behavior is physics, not fashion. Full camber boards with carbon stringers resist chatter and hold a line on ice. Rocker first boards smear beautifully until the surface hardens, then they wash. The Snowcat's camber came from mass placement and stiffness, its stringers from rails and track backing. Edge hold became track pressure continuity. The irony was inescapable. Metallurgy closed the loop. Higher yield strength steels with proper heat treatment blunted stress risers. Sudden load transfers at a crevasse lip create notches in effect, pushing local strain above average. Poor steel yields there, then work hardens into a brittle hazard. Good steel absorbs and redistributes, refusing to carry yesterday's scar into tomorrow's shock. The difference is invisible in a shop. It announces itself on blue ice. Reliability followed a chain, not a part. Oversized bearings ran cooler, kept oil films intact at the flanks, and held alignment so tooth load distribution stayed even during hits. Oil that doesn't shear maintains separation. Gears that don't micro-pit don't shed particles. Particles that don't circulate don't sandblast the next surface. The cascade reversed, away from failure. System integration made the weight earn its keep. Mass sat where it maintained track pressure, protected the driveline, and fed the dampers with the time they needed to work. Nothing floated. Everything tied back to contact continuity and torque smoothing. The mini payoff was simple. The machine looked excessive because its parts were sized for the worst 5 minutes of their life, not the average day. The lesson was harsh but clear. Now comes the ledger that matters: service logs, failure curves, and the crossing itself, where narratives gave way to numbers. When ideology stepped aside, the logs took over. Operators recorded track slip percentage, gearbox temperature, vibration spectra sampled at fixed intervals, fuel consumption under sustained load, and weld inspections after the crossing. Nothing anecdotal, just traces of what the machines actually did when the surface turned hostile. The measurement regime mattered because the Glacier punished spikes, not averages. Track slip told you when contact failed. Gearbox temperature revealed friction that oil films could no longer hide. Vibration spectra showed torsion traveling through the frame. Fuel burn under load captured the true penalty for staying planted. Weld inspections stamped the structural cost in cracks, or the lack of them. Each metric had a failure attached to it. European vehicles posted strong fuel numbers per kilometer. The scale of the advantage was consistent across the approaches and early miles. But variance rose the moment crevasse zones began. Traction wandered, slip percentages widened, and thermal spikes appeared during abrupt load returns. The numbers drew a jagged line. Efficiency remained, but it came with volatility. Incident logs filled in the gaps. Minor collapses over microbridges produced lateral whips, fast side loads that forced shutdowns. Recovery attempts multiplied, dragging out exposure time in the danger corridor. Each stop-start cycle reset the risk, inviting a fresh shock through drivelines and frames. What saved diesel cost minutes. What cost minutes increased hazard. This wasn't the only time a machine dismissed on paper proved itself under real conditions. The next story follows the same pattern.